The universe, as we understand it today, extends across approximately 93 billion light-years of observable space, containing structures that range from subatomic particles to galaxy superclusters spanning hundreds of millions of light-years. This vast expanse emerged from conditions that existed roughly 13.8 billion years ago, a figure derived from multiple independent lines of evidence, including the cosmic microwave background radiation, the observed expansion rate of space, and the ages of the oldest known stellar populations. The precision of this dating, now refined to within about 1% uncertainty, represents one of the more remarkable achievements of observational cosmology, though it remains important to note that this age applies specifically to the observable universe, and says nothing definitive about whether space extends infinitely beyond our cosmic horizon, or whether other regions might have emerged from different initial conditions. The earliest moments after what is conventionally called the Big Bang remain partially obscured from direct observation, not because of technological limitations alone, but because of fundamental physical constraints. During the first several 100,000 years, the universe existed as a dense plasma in which photons could not travel freely, scattering continuously off charged particles in a fog of ionized matter. Only when temperatures dropped sufficiently for electrons to combine with protons and helium nuclei, forming neutral atoms, did light begin to propagate unimpeded across cosmic distances. This transition, sometimes called recombination, despite electrons and nuclei having never been combined before, released the radiation we now detect as the cosmic microwave background, a snapshot of the universe at approximately 380,000 years after its origin. Every direction we look in the sky reveals this ancient light, now stretched by the expansion of space from its original visible light wavelengths to microwave frequencies, carrying information about conditions when the universe was roughly 1,000 times smaller and 3,000 times hotter than it is today. The uniformity of this background radiation, consistent to about 1 part in 100,000 across the entire sky, presents both a confirmation and a puzzle. The confirmation lies in demonstrating that the early universe was indeed a hot, dense, and remarkably homogeneous medium, precisely as predicted by the standard cosmological model. The puzzle emerges when we consider that regions on opposite sides of the sky, as seen from Earth, were never in causal contact during the conventional expansion history, meaning they had no opportunity to exchange information or energy that would explain why they arrived at nearly identical temperatures. This horizon problem, as it came to be known, provided one of the motivations for the development of inflationary cosmology in the early 1980s, a theoretical framework proposing that the universe underwent a brief but extraordinarily rapid exponential expansion during its first fraction of a second. Under this scenario, regions that appear causally disconnected today were actually in contact before inflation stretched them apart faster than light could travel, explaining their similar properties as a consequence of their shared origin rather than coincidental fine-tuning. Inflation, while not yet directly confirmed by observation, makes several predictions that have proven consistent with data, including the near flatness of space on large scales, and the specific statistical properties of the tiny temperature variations in the cosmic microwave background. These minute fluctuations, amounting to differences of only tens of millionths of a degree, carry encoded information about the physical processes operating in the early universe, and, perhaps more remarkably, about the quantum fluctuations that inflation would have amplified from microscopic scales to cosmic ones. The pattern of these fluctuations, analysed through sophisticated statistical techniques, reveals that the early universe had slightly more matter in some regions than others, providing the seeds around which all subsequent structure would form. Without these initial density variations, gravity would have had no concentrations to amplify, and the universe would have expanded into a featureless, uniform void, never producing galaxies, stars, planets, or any of the complex structures we observe today. The process by which these tiny primordial density variations grew into galaxies and larger structures spans billions of years and involves the interplay of gravity, gas dynamics, radiation pressure, and the still mysterious substance known as dark matter. Ordinary matter, the protons, neutrons, and electrons that constitute all visible objects, represents only about 5% of the total energy content of the universe, Dark matter, detectable only through its gravitational effects on visible matter and light, comprises approximately 27%. The remaining 68% consists of dark energy, a form of energy associated with empty space itself that causes the expansion of the universe to accelerate rather than slow down. These proportions, determined through observations of the cosmic microwave background, the large-scale distribution of galaxies, and the apparent brightness of distant supernova, represent one of the more surprising discoveries of late 20th century cosmology, fundamentally revising our understanding of what the universe contains and how it will evolve in the future. Dark matter's role in structure formation proves essential because ordinary matter alone could not have produced galaxies within the available time. Immediately after recombination, when atoms first formed and the cosmic microwave background was released, the temperature fluctuations in the radiation corresponded to density fluctuations in the matter of only about 1 part in 100,000. Ordinary matter, still coupled to radiation through residual interactions, was prevented from collapsing gravitationally by the outward pressure of the photons it contained. Dark matter, interacting only through gravity and experiencing no pressure from light, could begin collapsing immediately, forming gravitationally bound structures called dark matter halos long before ordinary matter was free to fall into them. When atoms finally decoupled from radiation and were able to respond to gravitational attraction, they fell into these pre-existing dark matter halos, where they could condense, cool, and eventually form the first stars and galaxies. Without dark matter's head start in structure formation, the universe would likely still be too uniform for galaxies to have appeared by the present day. The first stars, sometimes called population 3 stars in astronomical nomenclature, formed under conditions drastically different from those governing star formation today. The early universe contained only hydrogen and helium in significant quantities, with trace amounts of lithium produced during the first few minutes after the Big Bang, but essentially no heavier elements. The absence of these heavier elements, which astronomers call metals regardless of their actual chemical properties, meant that primordial gas clouds cooled inefficiently compared to present-day molecular clouds. Cooling is essential for gravitational collapse because it allows gas to radiate away the energy gained from contraction, preventing pressure from building up and halting further compression. The limited cooling pathways available to pure hydrogen and helium gas produced characteristic mass scales for the first stars that were substantially larger than typical stellar masses today, with theoretical models suggesting that many of these first stars exceeded 100 solar masses, and some may have reached several hundred solar masses. Stars of such enormous mass burn through their nuclear fuel rapidly, living only a few million years before exhausting the hydrogen in their cores and progressing through successive stages of nuclear burning. In the most massive cases, this sequence ends in catastrophic collapse and explosion as a supernova, or possibly as an even more energetic event called a pair instability supernova, in which the core becomes so hot that photons convert spontaneously into electron-positron pairs, reducing the radiation pressure that supports the star against gravity and triggering runaway collapse. These explosions disperse the first heavy elements into the surrounding gas, enriching the primordial medium with carbon, oxygen, iron, and other products of nuclear fusion and explosive nucleosynthesis. This material would be incorporated into subsequent generations of stars, and the heavy elements would themselves provide new cooling pathways that allowed smaller, longer-lived stars to form. Every element heavier than lithium in the present universe, including the carbon in organic molecules, the oxygen we breathe, the iron in blood hemoglobin, and the silicon in computer processors, was synthesized in stellar interiors or stellar explosions. A realization that fundamentally connects the existence of complex chemistry and biology to the life cycles of stars. The deaths of massive stars produce more than just dispersed heavy elements. They also leave behind compact remnants whose properties push the boundaries of known physics. Stars between roughly 8 and 25 solar masses typically end as neutron stars. Objects containing more mass than the Sun compressed into spheres only about 20 kilometers in diameter. At these densities, matter exists in forms unknown in any laboratory, with atomic nuclei squeezed together until they merge into a continuous fluid of neutrons, and possibly more exotic states involving strange quarks, or other forms of degenerate matter. The internal structure of neutron stars remains an active area of research, with different theoretical models predicting different relationships between mass and radius, different maximum masses before collapse to a black hole becomes unavoidable, and different behaviours during the mergers of neutron-star pairs. The detection of gravitational waves from such mergers, first achieved in 2017, opened a new window onto these extreme environments, providing constraints on the equation of state of ultra-dense matter that were previously inaccessible through electromagnetic observations alone. Black holes, formed from the collapse of the most massive stellar cores or through other mechanisms yet to be fully understood, represent perhaps the most extreme objects in the universe, regions where space-time curvature becomes so intense that light cannot escape, and our conventional notions of space and time break down. The boundary of a black hole, called the event horizon, marks the point of no return for anything falling inward, though it is not a physical surface but rather a mathematically defined region, beyond which outgoing light rays cannot propagate. Stellar mass black holes, those formed from collapsed stars, typically range from about 5 to a few tens of solar masses, while supermassive black holes found at the centres of galaxies span millions to billions of solar masses. The origin of these supermassive objects remains debated, with proposed mechanisms including the direct collapse of massive primordial gas clouds, the runaway merger of stellar mass black holes in dense star clusters, and the growth of intermediate mass seeds through prolonged gas accretion. Observations of quasars, the luminous nuclei of distant galaxies powered by material falling into supermassive black holes, reveal that such objects already existed when the universe was less than 1 billion years old. This observation poses a challenge for theories of black hole formation and growth, since conventional accretion processes have physical limits on how quickly mass can accumulate. The Eddington limit, named after the British astrophysicist Arthur Eddington, describes the maximum luminosity a gravitating object can sustain before radiation pressure blows away incoming material, effectively capping the rate at which a black hole can grow through standard accretion. For the most distant known quasars to have reached their observed masses within the available time, their growth must have been remarkably efficient, or they must have formed with unusually massive seeds, or both. Current theoretical work explores various combinations of rapid early growth, super Eddington accretion episodes, and direct collapse formation pathways, though no consensus has emerged on which mechanisms dominated in the early universe. The relationship between supermassive black holes and their host galaxies represents one of the more unexpected discoveries of recent decades. Observations reveal correlations between black hole mass and various properties of the surrounding galaxy, including the mass and velocity dispersion of stars in the central bulge. These correlations are surprisingly tight given that the black hole, despite its enormous mass, represents only about 1/1000th of the stellar mass in a typical galaxy, and directly influences only a tiny fraction of the galaxy's volume. The existence of such correlations implies that black holes and galaxies somehow regulate each other's growth, evolving together through processes that must involve energy and momentum transfer across vast differences in scale. Proposed mechanisms include feedback from accreting black holes, which can drive powerful jets and winds capable of heating or expelling the surrounding gas, thereby suppressing star formation and limiting both black hole growth and the accumulation of stellar mass. These feedback processes may explain why the most massive galaxies contain relatively old stellar populations with limited ongoing star formation, their gas reservoirs having been disrupted or ejected by earlier episodes of black hole activity. Galaxy evolution more broadly involves a complex interplay of processes including star formation, gas inflows, outflows driven by supernovae and black holes, and interactions with other galaxies. The Milky Way, our home galaxy, provides a laboratory for studying these processes in unusual detail, since we can observe individual stars, map gas distributions, and trace chemical abundances across the galactic disk and halo. Archaeological approaches to galactic history, sometimes called galactic archaeology, use the chemical compositions and orbital properties of stars as fossils recording past events, including ancient mergers with smaller galaxies that contributed some of the oldest stellar populations now found in the Milky Way's halo. Data from the Gaia Space Telescope, which has measured precise positions and motions for over 1 billion stars, has revealed that the Milky Way's history includes several significant merger events, the most recent of which, involving a galaxy sometimes called Gaia Enceladus or the Gaia Sausage, occurred roughly 10 billion years ago and contributed a substantial fraction of the stars currently found in the interstellar halo. The large-scale distribution of galaxies across the universe reveals a distinctive pattern known as the cosmic web, in which galaxies are not scattered randomly, but instead congregate along filaments and walls surrounding vast empty regions called voids. This structure emerges naturally from gravitational amplification of the primordial density fluctuations, as matter flows from underdense regions toward overdense ones, stretching the intervening space into elongated structures that persist over billions of years. The intersections of filaments mark the locations of galaxy clusters, the largest gravitationally bound objects in the universe, containing hundreds or thousands of galaxies, along with vast quantities of hot gas and dark matter. These clusters grow by accreting material from their surroundings, including smaller galaxy groups that fall along filaments and merge with the main cluster, adding their members to the growing population. The infall of galaxies into cluster environments subjects them to various disruptive processes, including gravitational tides that strip away outer stars and ram pressure from the hot intra-cluster gas that removes cold gas from galactic disks, transforming spiral galaxies into gas-poor ellipticals over cosmologically short timescales. The study of galaxy clusters has contributed significantly to our understanding of dark matter, since clusters provide environments where the gravitational effects of this invisible substance can be observed with particular clarity. One of the most striking demonstrations came from observations of the Bullet Cluster, a system in which two galaxy clusters have recently passed through each other, separating their different components in ways that reveal their distinct behaviours. The hot gas in each cluster, comprising most of the ordinary matter, interacted with the gas from the other cluster, slowing through electromagnetic interactions and remaining concentrated near the point of collision. The galaxies, which interact only rarely due to their small sizes relative to cluster dimensions, pass through each other with minimal disruption and continued outward from the collision site. Gravitational lensing observations, which map the distribution of mass through its effects on light from background galaxies, showed that most of the mass in the system is located with the galaxies rather than with the gas, exactly as expected if dark matter dominates the mass budget and interacts only gravitationally. This observation provided particularly compelling evidence against modified gravity alternatives to dark matter, which would predict that the gravitational lensing should follow the distribution of ordinary matter rather than appearing separated from it. The phenomenon of gravitational lensing, first predicted by Einstein's general theory of relativity and first observed in 1919 during a solar eclipse, has become a powerful tool for probing the distribution of matter throughout the universe. When light from distant sources passes near massive objects, the curvature of space-time bends the light paths, producing effects ranging from slight distortions in the shapes of background galaxies to dramatic multiple images and arcs when the alignment is particularly precise. By measuring these distortions statistically across large areas of sky, astronomers can map the distribution of matter, including dark matter, in 3 dimensions, tracing the cosmic web and measuring the growth of structure over cosmic time. These measurements provide independent constraints on cosmological parameters, including the amount of dark matter and dark energy, that can be compared with results from the cosmic microwave background and other probes. Minor tensions between different measurement methods, particularly regarding the current expansion rate of the universe, have attracted considerable attention and may point to new physics beyond the standard cosmological model, though systematic uncertainties in the various measurements have not yet been definitively ruled out as the explanation. The expansion of the universe, first observed by Edwin Hubble in the late 1920s through measurements of galaxy distances and redshifts, remains one of the foundational observations of modern cosmology. Distant galaxies appear shifted toward longer, redder wavelengths compared to nearby ones, with the amount of shift proportional to distance, exactly as expected if space itself is expanding and carrying galaxies apart like dots on an inflating balloon. The proportionality constant, called the Hubble constant, determines the current rate of expansion and, combined with other measurements, constrains the age and composition of the universe, Measurements of this constant through different methods have converged over decades from initial estimates spanning a factor of 2 to current values, agreeing within about 10%, but a persistent discrepancy of roughly 10% between methods based on the cosmic microwave background and methods based on the cosmic distance ladder has resisted explanation. The distance ladder approach uses nearby standard candles, including Cepheid variable stars and type Ia supernovae, to calibrate distances to remote galaxies, while the microwave background approach uses the physics of the early universe to predict the expansion rate based on the observed temperature fluctuations. Whether the tension reflects unrecognized systematic errors, new physics modifying the expansion history, or some combination remains an open question at the forefront of cosmological research. Type Ia supernovae. The explosions used as standard candles for measuring cosmic distances result from a completely different mechanism than the core collapse supernovae discussed earlier in connection with massive stars. These events occur in binary star systems containing at least one white dwarf, the compact remnant left when a sun-like star exhausts its nuclear fuel and sheds its outer layers. When mass transfers from a companion star onto the white dwarf, or when two white dwarfs merge, the accumulated material can trigger thermonuclear ignition, burning the entire star in a runaway fusion reaction that produces enormous quantities of nickel-56 and releases energy equivalent to billions of solar luminosities. Because the explosion mechanism involves a well-defined physical process related to the structure of white dwarfs, these events produce relatively uniform peak brightnesses that can be calibrated to serve as distance indicators. The discovery in the late 1990s that distant type YR supernovae appeared fainter than expected, indicating that the expansion of the universe is accelerating rather than decelerating, led directly to the inference of dark energy, and earned its discoverers the 2011 Nobel Prize in Physics. The cause of this acceleration remains unknown, with possibilities ranging from a cosmological constant, representing the energy of empty space, to dynamical fields that evolve over cosmic time, to modifications of general relativity on cosmological scales. The future evolution of the universe depends critically on the properties of dark energy, which in turn remain poorly constrained by current observations. If dark energy behaves as a cosmological constant, with unchanging energy density as space expands, the acceleration will continue indefinitely, eventually isolating gravitationally bound structures like our local group of galaxies within expanding bubbles of empty space. Objects beyond our local gravitational territory will recede faster and faster, their light progressively redshifted until they fade from view entirely, leaving future observers in an increasingly isolated and dark cosmos. If dark energy density increases with time, a possibility called phantom dark energy, the acceleration could eventually become so severe that gravitationally bound systems, stars, planets, and even atomic nuclei are torn apart in a catastrophic Big Rip scenario. Alternatively, dark energy might decay or reverse sign, potentially leading to a reversal of expansion and eventual recollapse. Current observations favour the cosmological constant interpretation, but cannot definitively distinguish among these possibilities, and next-generation surveys designed to measure dark energy's properties with greater precision remain among the highest priorities in observational cosmology. Stars, while contributing only a modest fraction of the total mass in the universe, remain the primary sources of light, and the sites where nuclear reactions transmute elements, generate energy, and drive the chemical evolution of galaxies. Stellar structure and evolution, established through more than a century of theoretical work and observational testing, provide a remarkably complete picture of how stars form, shine, and eventually die, though important uncertainties remain regarding processes like convective mixing, mass loss, and nuclear reaction rates. The Sun, an ordinary main sequence star roughly halfway through its hydrogen-burning lifetime, exemplifies the equilibrium between gravity's inward pull and the outward pressure from energy released by nuclear fusion in the core. For roughly 10 billion years, solar-type stars convert hydrogen into helium at rates that depend primarily on mass and composition, with more massive stars burning faster and dying younger. The most massive stars known, exceeding 100 solar masses, may live only a few million years before exhausting their fuel, while red dwarfs less than half the Sun's mass could continue shining for trillions of years, far longer than the current age of the universe. The final stages of stellar evolution depend critically on an initial mass, with low-mass stars ending as white dwarfs, surrounded by planetary nebulae, intermediate-mass stars also producing white dwarfs, but with more dramatic mass loss during the asymptotic giant branch phase, and high-mass stars exploding as supernovae that may leave behind neutron stars or black holes. These endpoints represent different physical conditions, from the electron degeneracy pressure that supports white dwarfs against gravity, to the neutron degeneracy and nuclear forces that stabilize neutron stars to the complete gravitational dominance within black holes. The transitions between these fates depend on mass thresholds that are not precisely known, with complications arising from binary interactions, rotation, magnetic fields, and metallicity. Binary stars, which comprise a significant fraction of all stellar systems, can experience mass transfer episodes that drastically alter their evolution, potentially stripping away envelope mass to produce different final states than single-star evolution would predict. Planetary systems form as a byproduct of star formation, emerging from the same molecular clouds that collapse to produce stars. As a cloud contracts under gravity, conservation of angular momentum causes it to spin faster, flattening into a disk around the nascent protostar. Within this protoplanetary disk, dust grains collide and stick together, gradually building larger aggregates that eventually grow massive enough to attract material gravitationally. The details of planet formation remain actively debated, with competing models emphasizing different growth mechanisms depending on distance from the star, disk properties, and timescales. Close to the star, where temperatures exceed the condensation points of volatile substances like water, primarily rocky material accumulates, potentially forming terrestrial planets like Earth. Farther out, beyond the snowline where water ice becomes stable, solid material is more abundant, facilitating the rapid growth of cores massive enough to gravitationally capture surrounding hydrogen and helium gas, and become giant planets like Jupiter and Saturn. The discovery of planets orbiting other stars, now numbering in the thousands, with many more candidates awaiting confirmation, has revealed planetary systems vastly more diverse than our own solar system suggested. Hot Jupiters, gas giant planets, orbiting their stars in just days or weeks, were among the first exoplanets detected because their gravitational effects on their host stars are large and their orbital periods are short, making them accessible to early detection methods. Their existence was initially surprising, since giant planets cannot form so close to their stars where temperatures are too high for volatiles to condense, implying that migration through the protoplanetary disk must have carried them inward after formation. Subsequent discoveries have found planets at essentially all orbital distances, from those grazing their stars' surfaces to those orbiting at hundreds of astronomical units, as well as planets spanning a continuous range of sizes from sub-Earth to super-Jupiter, including a population of planets intermediate in size between Earth and Neptune that have no analogue in our own system. The search for potentially habitable worlds focuses primarily on rocky planets within the habitable zones of their stars, the range of distances where temperatures might permit liquid water to exist on a planetary surface. This concept, while useful as a first approximation, oversimplifies the actual requirements for habitability, which depend on atmospheric composition, surface pressure, planetary magnetic fields, stellar activity levels, and numerous other factors. Mars, for example, lies within the Sun's habitable zone, but lacks sufficient atmospheric pressure for liquid water to persist on its surface today, while Venus, though at the inner edge of the habitable zone, experienced a runaway greenhouse effect that produced surface temperatures hot enough to melt lead. Understanding which planets might actually support liquid water, or more ambitiously life, requires detailed knowledge of planetary atmospheres and interiors that remains difficult to obtain for distant exoplanets. Atmospheric characterization of exoplanets has advanced significantly through transit observations, in which a planet passing in front of its star allows starlight to filter through the planetary atmosphere, imprinting spectral signatures that reveal the presence of various molecules. This technique works best for planets orbiting close to their stars, which transit more frequently, and for planets around smaller stars, where the planet blocks a larger fraction of the stellar disk. Early atmospheric detections focused on hot Jupiters, whose extended atmospheres produce stronger signals, identifying species like sodium, water vapor, and even evidence of escaping hydrogen gas. More recently, observations have begun probing the atmospheres of smaller, potentially rocky planets, though the signals are much weaker and require long observation times with the most sensitive available instruments. The James Webb Space Telescope, launched in late 2021, has expanded capabilities in this direction, detecting atmospheric constituents on planets down to roughly Earth-sized and providing the first detailed spectra of temperate rocky worlds. The possibility of life beyond Earth motivates much of the interest in exoplanet research, though the scientific study of this question faces fundamental challenges related to our limited understanding of life's origin and the difficulty of detecting biological signatures at interstellar distances. Life on Earth appears to have arisen relatively quickly on geological timescales, with possible evidence for microbial activity appearing in rocks dating to within a few 100 million years after the end of the late heavy bombardment, when conditions on the surface first became stable enough to support liquid water. This rapid emergence has suggested to some researchers that life may be common wherever conditions permit, though counter-arguments note that we cannot draw reliable statistical conclusions from a single example, and that survivorship bias may colour our perception. If life typically takes much longer to arise than the time available on early Earth, the fact that we exist would still be explained by anthropic selection, since we could only observe a universe in which life happened to appear on at least one planet. The nature of life's origin remains one of the more profound, unsolved problems in science, with competing hypotheses locating the critical transitions in various environments, from shallow warm ponds to deep-sea hydrothermal vents to interstellar space. The transition from prebiotic chemistry to self-sustaining biological systems required establishing the fundamental features common to all known life, including information storage in nucleic acids, catalysis by proteins, and energy metabolism through redox reactions. The interdependence of these systems poses a chicken and egg problem, since proteins are required to replicate nucleic acids while nucleic acids are required to encode proteins. The RNA world hypothesis proposes a resolution in which RNA, capable of both storing genetic information and catalyzing chemical reactions, served as the original molecule of life before proteins and DNA evolved as specialized improvements. Experimental work has demonstrated that RNA can indeed catalyze various reactions, including self-replication under certain conditions, lending support to this scenario, though the spontaneous formation of RNA in prebiotic environments remains challenging to explain given the complexity of its synthesis. Earth's geological history provides the context for understanding how life evolved from its microbial origins to the present diversity, including the conditions that made complex multicellular life possible. For roughly the first 2 billion years, life remained exclusively microbial, dominated by prokaryotes and early single-celled eukaryotes. Oxygen, now comprising about 21% of Earth's atmosphere, was initially present only in trace amounts produced by photosynthetic cyanobacteria, but consumed by reactions with reduced minerals and volcanic gases faster than it could accumulate. The Great Oxidation Event roughly 2.4 billion years ago marks the point when oxygen production finally exceeded these sinks, allowing molecular oxygen to build up in the atmosphere and ocean. This transition had profound consequences for Earth's chemistry, geology and biology, rusting iron out of the oceans to form banded iron formations, enabling new metabolic pathways based on aerobic respiration, and likely triggering a global glaciation, as oxygen destroyed atmospheric methane that had been providing greenhouse warming. The rise of atmospheric oxygen set the stage for the evolution of complex eukaryotic cells with mitochondria, organelles derived from once free-living bacteria that became symbionts within larger cells. This endosymbiotic event, which also gave rise to chloroplasts and photosynthetic eukaryotes, represented a fundamental innovation in cellular organization, enabling eukaryotes to achieve larger sizes and more complex metabolisms than prokaryotes could support. The transition to multicellularity occurred independently in multiple eukaryotic lineages, including animals, plants, fungi, and several groups of algae, suggesting that whatever advantages multicellularity confers were discovered repeatedly once the appropriate cellular machinery was in place. The selective advantages may have included increased size for predator avoidance, division of labour among specialised cell types, and extended lifespan through reproduction by specialised reproductive cells, while somatic cells handle other functions. The Cambrian explosion, roughly 540 million years ago, marks a dramatic apparent acceleration in the diversification of animal body plans, with most major animal phyla appearing in the fossil record within a geologically brief interval of perhaps 20 million years. The causes of this rapid diversification remain debated, with proposed factors including rising oxygen levels that permitted larger body sizes and more active lifestyles, the evolution of eyes that created new selective pressures for predation and defense, the colonization of new ecological niches, and developmental genetic innovations that allowed greater morphological experimentation. The quality of the Cambrian fossil record, including exceptional preservation sites like the Burgess Shale that capture soft-bodied organisms normally lost to decay, may also contribute to the apparent suddenness by providing a clearer window on diversity that had been accumulating earlier but leaving fewer traces. Mass extinctions have repeatedly pruned the tree of life, eliminating large fractions of species and allowing survivors to radiate into vacated ecological niches. The largest known extinction, at the end of the Permian period roughly 252 million years ago, eliminated perhaps 90% of marine species and 70% of terrestrial vertebrate species. The causes likely involved massive volcanic eruptions in what is now Siberia, which released carbon dioxide driving global warming, sulfur dioxide causing acid rain, and possibly halogen compounds that damaged the ozone layer. The end Cretaceous extinction, roughly 66 million years ago, famously eliminated the non-avian dinosaurs along with many other groups, and has been convincingly linked to an asteroid impact in what is now the Yucatan Peninsula, though contemporaneous volcanism in India may have contributed to environmental stress. These extinctions illustrate both the vulnerability of complex life to catastrophic environmental changes and its resilience in recovering and rediversifying given sufficient time. The evolution of intelligence and technology on Earth represents a particular sequence of developments whose generality remains unknown. The expansion of brain size in the hominin lineage over the past several million years, culminating in anatomically modern humans roughly 300,000 years ago, correlates with increasingly sophisticated tool use, social organization, and eventually symbolic thought and language. The causes of this expansion remain debated, with proposed drivers including the demands of social living, the cognitive requirements of tool manufacture and use, dietary shifts associated with cooking and meat consumption, and various feedback loops among these factors. The transition to behaviourally modern humans, marked by evidence of art, personal ornamentation, and long-distance trade, appears to have occurred more recently, perhaps within the past 100,000 years. Though dating remains uncertain, and definitions of behavioural modernity vary among researchers. The development of agriculture, roughly 10,000 years ago, fundamentally transformed human societies, enabling population growth, sedentary settlement, occupational specialisation, and eventually the emergence of cities, writing, and the complex social structures characteristic of civilization. These developments occurred independently in several locations, including the Fertile Crescent, China, Mesoamerica, and the Andes, suggesting that the transition from hunting and gathering to farming and herding represented a response to common selective pressures, rather than a singular invention that spread from a single source. The pressures may have included population growth that strained foraging resources, climate changes at the end of the last ice age that favoured certain plant species suitable for domestication, and social changes that created incentives for intensified food production. Once established, agricultural societies tended to expand at the expense of foragers, not necessarily through conquest, but through sheer demographic pressure as larger populations displaced smaller ones. The development of science and technology as systematic enterprises, rather than isolated innovations, represents a more recent historical phenomenon whose origins are subject to ongoing scholarly debate. The scientific revolution of the 16th and 17th centuries in Europe established new methods of empirical investigation, mathematical description, and experimental testing that proved extraordinarily productive at generating reliable knowledge about the natural world. Why these developments occurred when and where they did, rather than earlier or elsewhere, has been explored from perspectives including institutional history, economic incentives, cultural values, and contingent historical circumstances. The Islamic world, China, and India all possess sophisticated traditions of natural philosophy and practical knowledge that in some respects exceeded European achievements of the same periods, yet did not produce the same systematic transformation into experimental science. Explanations range from the competitive political fragmentation of Europe, which prevented any central authority from suppressing innovation, to the specific theological and philosophical frameworks that made nature appear as a lawful system accessible to human reason, to purely contingent factors involving individual genius and fortunate institutional configurations. The application of scientific knowledge to technology, often called the Industrial Revolution though occurring in stages rather than as a single event, transformed material conditions of life more dramatically than any previous development in human history. Beginning in Britain in the mid-18th century and spreading gradually to other regions, industrialization multiplied productive capacity through the harnessing of inanimate energy sources, first water and coal, later petroleum and electricity, now increasingly renewable sources. The consequences included urbanization, population growth, rising living standards, environmental degradation, and shifts in political and economic power that continue to reshape global relations. The ability to extract and transform natural resources at unprecedented scales has made humanity a geological force, altering the composition of the atmosphere, acidifying the oceans, and driving species extinctions at rates comparable to the mass extinctions of the geological past. Understanding the universe, from the cosmic microwave background to the conditions for life, requires integrating knowledge across disciplines ranging from particle physics to biology to the social sciences. The elements synthesized in stellar interiors constitute the building blocks of planets and organisms. The energy released by nuclear fusion in stars drives planetary climates and photosynthesis. The expansion of the universe sets the timescales available for evolution. And the specific conditions on Earth, including its distance from the Sun, its inventory of water and volatiles, its tectonic activity, and its magnetic field, have all shaped the trajectory of life's development. These connections, spanning scales from subatomic to cosmological, represent one of the more remarkable features of modern scientific understanding, revealing a universe in which apparently disparate phenomena are linked by underlying physical processes. The cosmic microwave background, discussed earlier as a fossil of the early universe, also provides information about the geometry and fate of the cosmos. The angular scale of the temperature fluctuations measured with increasingly precise instruments, from ground-based observatories, balloon-borne experiments, and space missions including COBE, WMAP, and Planck, constrains the curvature of space. If the universe were positively curved like the surface of a sphere, the fluctuations would appear larger on the sky than expected for flat space. If negatively curved like a saddle, they would appear smaller. Observations consistently indicate that space is very close to flat, meaning that the sum of angles in a cosmic triangle equals 180 degrees to within the precision of measurement. This flatness has implications for the total energy content of the universe, and, as mentioned earlier, provided motivation for inflationary cosmology, which naturally produces a flat universe regardless of initial conditions. The accelerating expansion driven by dark energy poses profound questions for the ultimate fate of the universe and for fundamental physics. If dark energy represents a cosmological constant, it can be understood as the energy of the vacuum, the residual energy of empty space after all particles and fields have been removed. Quantum field theory predicts that such vacuum energy should exist, arising from the zero-point fluctuations of quantum fields, but the predicted magnitude exceeds the observed value by roughly 120 orders of magnitude, one of the largest discrepancies between theoretical prediction and observation in all of physics. This cosmological constant problem suggests that our understanding of the quantum vacuum is fundamentally incomplete, possibly requiring new physics at energy scales inaccessible to current experiments. Alternative explanations for cosmic acceleration invoke dynamical fields rather than a constant energy density. These models, collectively called quintessence after the classical fifth element, propose that a new scalar field permeates the universe, with properties that cause it to drive accelerated expansion at late times. The field could evolve over cosmic history, potentially explaining why acceleration began only relatively recently in cosmic terms, when the universe was already more than half its current age. Distinguishing between a cosmological constant and dynamical dark energy requires measuring the expansion history and the growth of structure with sufficient precision to detect any time evolution, a goal that motivates next-generation surveys including the Dark Energy Spectroscopic Instrument, the Vera Rubin Observatory, and the Euclid Space Mission. Gravitational waves, ripples in spacetime predicted by general relativity and first directly detected in 2015, open a new channel for observing the universe that is fundamentally different from electromagnetic radiation. While light is produced by charged particles and interacts with matter, allowing it to be absorbed, scattered, or blocked, gravitational waves are produced by accelerating masses and pass through matter, essentially unimpeded. This transparency means that gravitational waves can carry information from regions and epochs that are opaque to electromagnetic observation, including the first moments after the Big Bang before the cosmic microwave background was released, the interiors of supernovae as they collapse, and the immediate vicinities of merging black holes. The detection of gravitational waves from binary black hole mergers revealed a population of black holes more massive than those previously known from X-ray observations, raising questions about how such massive stellar remnants form. Subsequent detections of neutron star mergers provided independent confirmation that such events produce heavy elements, including gold and platinum, through rapid neutron capture nucleosynthesis, directly observing the astrophysical source of elements that had been predicted theoretically but never confirmed observationally. The network of gravitational wave detectors continues to expand in sensitivity and geographic coverage, with improved versions of LIGO in the United States, Virgo in Italy, and Kagra in Japan, joined by planned facilities in India and potentially other locations. Space-based detectors, sensitive to lower frequencies than ground-based instruments can access, would open additional windows on gravitational wave sources including supermassive black hole binaries, compact binaries in the Milky Way, and possibly signals from the early universe. The Laser Interferometer Space Antenna, a European Space Agency mission with NASA participation, is planned for launch in the 2030s and would position 3 spacecraft in a triangular formation millions of kilometers apart, measuring distance changes as tiny as picometers to detect passing gravitational waves. Multi-messenger astronomy, combining gravitational wave observations with electromagnetic and neutrino detections from the same sources, has already demonstrated its power through the observation of the neutron star merger G170817. Gravitational waves detected by LIGO and Virgo triggered searches across the electromagnetic spectrum, revealing a short gamma-ray burst, an optical transient called a kilonova, an emission across wavelengths from radio to X-ray that persisted for months. This event provided confirmation that neutron star mergers produce short gamma-ray bursts, a connection that had been suspected but not proven. Demonstrated that heavy element synthesis occurs in these environments, as the kilonova emission matched theoretical predictions for the radioactive decay of newly synthesized elements, and allowed an independent measurement of the Hubble constant through the combination of gravitational wave and electromagnetic data, providing a standard siren measurement that avoids the systematic uncertainties affecting traditional distance ladder approaches. The detection of high-energy neutrinos from cosmic sources adds another dimension to multi-messenger astronomy. Neutrinos, produced in nuclear reactions and particle physics processes, interact so weakly with matter that they escape from dense environments where light cannot penetrate, carrying information about conditions in stellar cores, supernova, and environments around accreting black holes. The IceCube Neutrino Observatory, a cubic kilometer detector frozen into the Antarctic ice, has identified neutrino sources including a blazar, an active galaxy with a relativistic jet pointed toward Earth, providing direct evidence that such jets are sites of cosmic ray acceleration. Cosmic rays themselves, charged particles arriving at Earth with energies up to 100 million times greater than those achievable in particle accelerators, have unknown origins for their highest energy members, with proposed sources including gamma-ray bursts, active galactic nuclei, and starburst galaxies. Identifying these sources requires combining arrival direction information with models of particle propagation through cosmic magnetic fields, which deflect charged particles and obscure the connection between detection direction and source location. The extreme energies of ultra-high energy cosmic rays pose challenges for physics as well as astrophysics. Particles exceeding about 50 million billion electron volts should lose energy rapidly through interactions with cosmic microwave background photons, limiting the distance from which they can arrive and implying that their sources must be relatively nearby on cosmological scales. The spectrum of arriving cosmic rays shows features consistent with this GZK cutoff, named after the physicists who predicted it. But the sources responsible for producing such extremely energetic particles remain unidentified. Acceleration mechanisms capable of reaching these energies require either extraordinarily strong magnetic fields, very large acceleration regions, or exotic physics beyond the standard model, and distinguishing among these possibilities requires better statistics on arrival directions and energies from next-generation observatories. The frontiers of fundamental physics, explored partly through cosmological observations and partly through laboratory experiments, include the unification of quantum mechanics and general relativity, the nature of dark matter, and the possible existence of additional dimensions of space. String theory, the leading candidate for a unified framework, posits that fundamental particles are actually tiny vibrating strings whose different oscillation modes correspond to different particle types. The theory requires additional spatial dimensions beyond the three we experience, curled up at scales too small to observe directly, and predicts a landscape of possible vacuum states whose number may exceed 10 to the power of 500. Whether any of these vacua corresponds to our universe, and whether the theory makes testable predictions that could distinguish it from alternatives, remain subjects of ongoing research and debate. The detection of dark matter particles, if they interact with ordinary matter through any force other than gravity, would revolutionize our understanding of the universe's composition. Experiments deep underground, shielded from cosmic rays, attempt to detect the rare interactions expected if dark matter consists of weakly interacting massive particles passing through the Earth. So far, no convincing signals have emerged, ruling out many theoretical candidates and pushing others to parameter ranges that will be difficult to probe. Alternative detection strategies include searching for dark matter annihilation or decay products in cosmic rays, gamma rays, or neutrinos, and looking for the effects of dark matter on gravitational wave observations or on the cosmic microwave background. The possibility remains that dark matter interacts only gravitationally, in which case direct detection would be essentially impossible with foreseeable technology, and its nature would need to be inferred entirely from its cosmological and astrophysical effects. The search for life beyond Earth extends from the direct exploration of solar system bodies to the remote observation of exoplanet atmospheres to the search for technological signatures from extraterrestrial civilizations. Mars, with its evidence of past water and possible subsurface liquid reservoirs, represents the most accessible target for astrobiological investigation, with missions including rovers and planned sample return aimed at searching for biosignatures in ancient rocks and potentially surviving organisms in protected niches. The icy moons of Jupiter and Saturn, including Europa, Enceladus, and Titan, possess subsurface oceans that may provide habitable environments shielded from surface radiation, though accessing these environments for direct sampling poses formidable engineering challenges. Titan, with its dense atmosphere, hydrocarbon lakes, and complex organic chemistry, represents a particularly intriguing environment where alternative biochemistries based on liquid methane rather than liquid water might conceivably have arisen, though no evidence for such life currently exists. Atmospheric biosignatures, chemical species whose presence in a planetary atmosphere would be difficult to explain through abiotic processes, provide a potential pathway for detecting life on distant exoplanets. Oxygen, in combination with methane, for example, represents a thermodynamic disequilibrium that biology maintains on Earth through continuous metabolic activity. In the absence of life, these gases would rapidly react and reach equilibrium at much lower concentrations. Other potential biosignatures include phosphine, recently detected in Venus's atmosphere and proposed as a possible biological signature, though the detection remains controversial, and abiotic explanations have been proposed. The challenge lies in distinguishing genuinely biological signals from exotic geochemistry or photochemistry that might produce similar molecules on alien worlds with different compositions and conditions. This challenge requires detailed modelling of planetary atmospheres, geochemistries, and potential false positives, work that remains in early stages but will become increasingly urgent as observations of temperate Earth-sized planets improve. The search for extraterrestrial intelligence through detection of technological signatures takes a different approach, looking not for the chemistry of life, but for the artifacts of technology. Radio searches conducted since the 1960s scan the sky for narrow-band signals too coherent to be produced by natural processes, while optical and infrared searches look for laser pulses or the waste heat of hypothetical megastructures. No convincing detections have occurred despite decades of searching, though the parameter space remains vast and largely unexplored. The interpretation of this null result depends on assumptions about the prevalence of technological civilizations, their longevity, their desire or need to produce detectable signals, and the sensitivity of our searches relative to typical signal strengths. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilization suggested by the vast number of stars and planets and the lack of evidence for their existence, has generated numerous proposed resolutions ranging from the difficulty of interstellar travel to the possibility that technological civilizations tend to destroy themselves, to the conjecture that we are among the first such civilizations to arise in the galaxy. The overview of the universe presented here, spanning from the first moments after the Big Bang to the speculative future of cosmic acceleration and the search for life, necessarily omits countless details, nuances, and active areas of research. Each topic mentioned could be expanded into its own extensive treatment, with subtleties and uncertainties that a survey cannot adequately convey. The nature of scientific knowledge, provisional and subject to revision as new observations challenge established understanding, means that some statements made here will likely require modification in light of future discoveries. The history of cosmology provides numerous examples of paradigm shifts that overturned previous consensus, from the realization that the universe extends beyond the Milky Way, to the discovery of cosmic expansion, to the inference of dark energy, and there is no reason to expect that our current understanding represents the final word. What remains remarkable is the degree to which humans, living on a small planet orbiting an ordinary star in an unremarkable corner of a typical galaxy, have been able to piece together a coherent picture of the universe's structure, composition, history, and probable fate. The methods developed over centuries of scientific investigation, combining mathematical reasoning, observational precision, experimental testing, and theoretical creativity, have proven extraordinarily effective at generating reliable knowledge about phenomena vastly removed from everyday human experience. Whether this success reflects something fundamental about the relationship between human cognition and the structure of reality, or whether it represents a contingent achievement that might not have occurred or might take different forms elsewhere, remains an open philosophical question. The universe itself, as revealed by these investigations, appears to be largely indifferent to human existence, operating according to physical laws that make no reference to observers or purposes. Yet within this vast and apparently purposeless cosmos, the emergence of life, intelligence, and technology on at least one planet demonstrates that complexity and meaning can arise from simple physical processes given sufficient time and the right conditions. Whether such emergence is common or rare, whether other observers elsewhere contemplate similar questions, and whether the human understanding of the cosmos will continue to deepen or will eventually encounter fundamental limits, remain to be discovered through ongoing exploration and investigation. The universe, in its immensity and complexity, continues to pose questions that human curiosity drives us to pursue, and the pursuit itself regardless of ultimate answers, represents one of the most distinctive achievements of our species,